Hey developers, welcome to Decoding. Today, we're bringing you the hottest open source projects trending on GitHub, so you don't miss any tech developments worth your attention.
Today, we're taking a deep dive into a trending project on GitHub, Hands-on Large Language Models, the official code repository for the O'Reilly book of the same name. With over 22,000 stars and nearly 500 more added just today, this Jupyter Notebook collection offers a rare combination of a professionally published book and hands-on runnable code, making it one of the most practical entry points for developers looking to truly understand and build with large language models. Here is a question worth sitting with for a moment. If you had to teach someone how a large language model actually works, not just how to use it, but how it thinks, how it processes a sentence, how it decides what word comes next, where would you even start? For most developers, that question has no clean answer. Theory lives in papers, code lives in GitHub repos, and neither speaks to the other. That gap is exactly what a project called Hands-on Large Language Models set out to close. Its 22,000 stars suggest it found a way. Hands-on Large Language Models is the official code repository for the O'Reilly book of the same name. It was authored by J. Alomar and Martin Grutendorst. J. Alomar is widely recognized for his illustrated blog series that made transformer architecture digestible for tens of thousands of engineers. Martin Grutendorst is the creator of Topic, a widely adopted topic modeling library. Together, they built what the community has come to call the Illustrated LLM book. The repository hosts 12 Jupyter notebooks, each mapped directly to a chapter in the book. It has accumulated 22,212 stars in total, with 469 added in a single day. There are also 5,192 forks, which is a strong signal that people are not just reading it, but actively working with it. Learning large language models has always had a structural problem. On one side, you have academic papers dense with equations, matrix math, and notation that requires a PhD to parse. On the other side, you have vendor documentation that tells you how to call an API, but not what happens after you do. Developers caught in the middle have had to stitch together a coherent understanding from blog posts, YouTube lectures, and Stack Overflow threads. Each one covers only a fragment of the picture. The deeper pain point is that LLM concepts are genuinely hard to visualize. An attention mechanism, for example, is not something you can intuit from a formula alone. You need to see how tokens attend to each other across layers, how embeddings cluster in high-dimensional space, how a fine-tuning loss curve actually behaves. Before projects like this one, that visual layer was almost entirely absent from practical learning resources. What hands-on large language models did differently is treat visualization as a first-class engineering artifact. The book ships with nearly 300 custom-made diagrams. The code repository then lets you run the concepts those diagrams explain. That creates a feedback loop between understanding and execution that neither a textbook nor a code dump alone can produce. The repository is organized around two fundamental classes of models that dominate the modern LLM landscape: representation models and generative models. Understanding the distinction matters because they are built for different jobs and fine-tuned in different ways. Representation models, the best known being BERT, are encoder-only architectures. Think of them as models that read and understand, rather than models that write. The notebooks covering text classification, text clustering, semantic search, and embedding creation all sit in this category. The key technology here is the Sentence Transformers library, which wraps pre-trained transformer models and turns them into dense vector generators. When you convert a sentence into a vector, you are compressing its meaning into a point in a mathematical space where similar ideas sit close together. The notebooks use tools like UMAP, a dimensionality reduction algorithm, to project those vectors onto a 2D plane. The result is that you can literally see clusters of related topics forming. It is one of the rare moments in machine learning education where the output is genuinely beautiful. Generative models, the GPT family-style architectures, handle the other half of the curriculum. Chapters on prompt engineering, advanced text generation, retrieval augmented generation, and generative model fine-tuning all live here. Prompt engineering is the craft of writing instructions that reliably steer a model toward useful outputs. Retrieval augmented generation, commonly called RAG, is a technique that connects a language model to an external knowledge base. Instead of relying solely on what was baked into the model during training, RAG lets the model look things up at inference time. That dramatically improves accuracy for domain-specific questions. The fine-tuning notebooks are particularly notable. They demonstrate how to take a pre-trained model and adapt it to a specific task using techniques like LoRA, which stands for Low Rank Adaptation. LoRA updates only a small fraction of a model's parameters rather than retraining from scratch. That makes fine-tuning feasible on consumer-grade hardware. Every notebook is optimized to run on Google Colab using a free T4 GPU, which carries 16 gigabytes of video memory. The one-click Open in Colab button removes the environment setup friction that kills so many self-directed learning attempts. The audience for this project is broader than the typical open-source repository. A back-end engineer who needs to add a semantic search feature to a product can go straight to the Chapter 8 notebook on RAG and have a working prototype within an afternoon. A data scientist building a document classification pipeline can use the BERT fine-tuning chapter as a template and adapt it to their own labeled dataset. Academic researchers have another entry point. The project serves as a reproducible baseline for NLP experiments. When you need to demonstrate that a new technique outperforms standard fine-tuning, having a clean, citable implementation of that baseline matters. Enterprise training programs are also a natural fit. The combination of visual aids and executable code makes it possible for an internal AI enablement team to run a structured workshop without building curriculum from scratch. The 5,000 plus forks suggest this is already happening. People are not just studying the notebooks, they are adapting them for internal use, which is a proxy for organizational adoption at scale. For anyone completely new to the field, Chapter 1 requires no prior LLM knowledge, and the progression is steep enough to hold the attention of someone who already knows what a transformer is. Now, the 22,000 stars represent real enthusiasm, but a few structural tensions are worth naming. The first is the gap between educational code and production code. Jupyter notebooks are excellent for learning and nearly useless for shipping software. Every pattern demonstrated here, from model loading to inference, would need to be refactored into modular, tested, observable Python packages before it could run in a real system. The project does not pretend otherwise, but learners sometimes miss that distinction. The second tension is the speed of the field versus the permanence of a book. O'Reilly books are written over months and printed on paper. The LLM landscape changes faster than any book can track. Some techniques covered here, like certain fine-tuning approaches, are already being superseded by newer methods. The bonus content folder attempts to address this with guides on Mamba, mixture of experts, and quantization. But the core curriculum is frozen. The third issue is hardware dependency. Despite the Colab optimization, certain chapters require GPU access that goes beyond what the free tier reliably provides. For learners in regions with poor internet or institutional restrictions on Google services, the experience degrades significantly. None of these are fatal flaws. They are the inherent limitations of a teaching artifact operating in a fast-moving domain. The question is whether the foundation it builds is durable enough to remain relevant as the field evolves. And the answer is mostly yes, because transformer fundamentals, embedding theory, and the logic of fine-tuning are unlikely to become obsolete even as specific implementations change. Hands-on large language models is one of the most complete attempts to bridge the gap between LLM theory and practice that currently exists in open source. Its combination of authoritative authorship, visual clarity, and executable notebooks makes it the closest thing to a reliable on-ramp for anyone serious about understanding how these systems work from the inside. If the question is where to start, this project is a defensible answer.
That's all for today's Devcovery. We hope these GitHub trending projects spark some inspiration for your development work. You can find all the repos mentioned in the description below. If you enjoyed this episode, don't forget to subscribe to our channel. See you tomorrow at the same time.